Okay, welcome to 10.5-2, Day 2, Volumes, Prisms, and Cylinders. And today we're comparing capacities. So capacity, the amount a container can hold. So a container could be any kind of container. How much cake mix can fit in here, right? How much dog food can fit in here? That is our definition of capacity. So the amount a container holds. A company wants to know which package holds more dog food. Figure A is a box. Figure B is a cylinder. Which one holds more dog food? What will we do? Well, we will find out how much it holds. And another word for that is volume. How do we find the volume of this figure A? It's a box. What type of figure is that? Rectangular prism. So we will use our formula for that. Jot it down. It is volume equals base area times height. What type of base does a rectangular prism have? A rectangle. So we will change base area to the formula for rectangle's area, little b times h. What side do you want to consider the bases of this figure? Most people like to use the bottom and top, so let's use that. So the base area has the dimensions of 8 inches times 3 inches, and the height of the prism is the distance between the two bases. You can see what it is. It's 8 inches. So we will multiply these values, and 8 times 3 is 24. 24 times 8 is 192 inches squared. I'm sorry, it's inches cubed, isn't it? We have inches times inches times inches. We have inches cubed, which makes sense. This is volume. We're talking 3 dimensions. Let's see figure B. What shape is figure B? It's a cylinder. So it's kind of like this can, right? It happens to be laying on its lateral surface. The bases are always the two congruent circles. So formula for the volume is the same as the prism, right? But because the base area is a circle, we can also write it this way, pi r squared times h. So let's substitute the values we have for r, and for h, the height is the distance between the two bases, and we end up with 2 inches squared for the radius and 16 inches for the height. 2 squared is 4, and 4 times 16 is 64. So we have 64 pi inches cubed. So we're at the point of needing to use some value for pi. What do we usually use? 3.14. So 64 times 3.14 is 200.96 inches cubed. So which container holds more dog food? Container B. Good. So we'll jot in our inequality sign. Oops, shoot. That's as good as I can do with this cursor. So there you go. The A figure is less than the B, or B is greater than A. Very good. Let's move on. We're now going to find the volume of a composite solid. Okay? So look at this solid. It's not the best picture, but what do these figures look like? These figures look like a small cylinder attached to a large cylinder. So when we have a composite figure, what do? We make a plan to add the pieces, and in some cases we subtract pieces. So in this case we're going to add pieces, a small cylinder and a large cylinder. So our plan would look something like this. The volume total equals the volume of the small cylinder plus the volume of the big cylinder. So we are going to need the formula for cylinders, aren't we? So let's go to the next step. How do you find the volume of a cylinder? We just did it. It's pi r squared times h. Good. So we have that happening twice. But remember, we have two different sized cylinders, so we're going to have to go up and substitute the correct values in. Let's start with the small cylinder on the left. What is the radius and height of this cylinder? You got it. The radius is 2 inches, and the height is the distance between the bases, 5 inches. So we can go down and substitute those values. And good, we have 2 inches squared times 5 inches. 2 inches squared is 4 inches squared. 4 inches squared times 5 inches is 4 times 5, 20 inches cubed, right? And we still have the pi. Don't forget the pi. We're going to work with that later, so let's leave it as it is in terms of pi. Going over to the big cylinder, we have our plan, but we need to know the radius and height of the big cylinder. So looking back up at our figure, we have a radius. It's hard to see. The height, you can see between the two bases, is 14 inches. Can you find the radius here? We have a distance of 4, and then we have this other cylinder, and another distance of 4. So it looks like we need to go halfway across the little cylinder, and halfway across the little cylinder is the radius we knew from the original small cylinder. So 4 plus 2 is 6. So this radius of the large cylinder is 6 inches, and the height is 14 inches. So we plug that into our formula, and we go ahead and multiply. 6 squared is 36, and 36 times 14 is 504. Don't forget we still have the pi. But because both of these terms have pi, they're both in terms of pi, they are like terms, so we can add them. 20 pi inches cubed plus 504 pi inches cubed is 524 pi inches cubed. So go ahead and multiply that by pi now, and we'll see this composite volume. 524 times 3.14 is 1,645.36 inches cubed. And do practice your multiplication with decimals. It will make you very strong. Okay, so there was our capacity, which just is another word for volume. And now we're going to try graphing a volume function, which is a little tricky. Kind of brings in some past graphing experience into our math today. So if you have two unknowns in the same equation, you have something that is graphable, right? We just need to find the points. So what did we do with equations? We first put them into function form, right? Remember, we isolated a variable. And then, it's the most basic way to find points, make a table. So we're going to simplify an equation, make a table, get some points, plot them on a graph, and then connect the points, right? Draw. So here is our triangular prism, which has a height of 8 inches and a base height of 4 inches. Graph the volume of the prism as a function of x equals the base of the base. The base of the base. That's probably the trickiest phrase in this problem. So how do we find the volume of a prism? V equals base area times height. Good. So the next step, what kind of base area does a triangular prism have? It has a triangle. So the area of a triangle is BH over 2. Good. So we've got area of a triangle times height for volume. What do we know from the word problem? The triangular prism has a height of 8 inches. So which height is that? The height of the prism. You got it. It's here, the height of the prism. And then it has a base height. So its base is a triangle. The triangle's height then is 4 inches. So that is here, the triangle's height. So substitute those values in carefully. Notice I'm also changing the base of the base, the triangle, to x, which is something that the problem asked us to do. I guess if you had a choice, you could keep it lowercase b, but because the problem asks us to change it to x, we'll change it to x. And so now, can we simplify this equation further? We can. There's 4x up here. X times 4 is the same as 4 times x. Can we divide 4x by 2? We can. So we have 2x, and out here we have 8 inches, right? So we could multiply 2 times x times 8. We can actually use the commutative property and bring that 8 over near the 2. What is 2 times 8? 16. Very good. So the most simple way to write this equation is the volume equals 16x times inches squared, right? That x is the unknown base of the base, right? So we are going to go over and create a table first. The input, the independent variable, is x. The output, depends on what we put in, is v, for volume. So let's choose some easy values for x. Since this is the real world, we wouldn't have a triangle with a negative length base, so we won't use any negatives, and we won't use 0. It doesn't make sense to have a triangle with a base of 0. It wouldn't exist. So let's start with the next easiest number, 1. So how about 1, 2, 3, 4? And so this is, again, the base of our triangle. It could vary, right? So when we plug 1 into our simple equation, we have 16 times 1, which is 16 inches cubed, right? The units would be cubed. When we plug in 2, 16 times 2 is 32. Plug in 3, 16 times 3 is 48. Plug in 4, 16 times 4 is, you got it, 64. Good. So we'll take this table of points over and we will graph it and see what it looks like. So again, our input, just like with our linear equations that we graphed, our input is usually found on the x-axis. It doesn't have to be, but we'll put it there. And so let's label the horizontal axis x and the vertical axis b, because that's the output in this example. So now we're just going to plot the points. Let me grab a pen. And we have, we're going to have to label where are these values, right? So I'm going to allow every 2 blue lines, I'm going to put a little hash mark on every 2, and I'm going to let them each have a unit of 1. So this here would be, say, 1, 2, 3, 4, 5. Let's see if I can draw 5. Good. And so, and in this direction, I'm actually going to have a different scale, because look at how big it gets with when x is 4, v is 64. So I want to make sure I can see that. So let me go way up here and put at the very top a hash mark, and I'll call that 64. Since that's the biggest one I am showing in my table, I'll just let that be seen here. And then halfway, let's see, 2, 4, 6, 8, 10, I think it's about here. Halfway is 32, right? And then halfway here, it's 2, 4, 5, that would be my 16. It so happens I'm able to label the very values that are in my table. And we've got 48 here. Okay, so you've got your tables all set up with just the first quadrant shown, because this is the real world, right? And often the real world is found in the first quadrant. So let's go to an x value of 1, so the triangle's base would be 1, and we have the volume of 16. Can you see that? 16. And when x is 2, the volume is 32. When x is 3, the volume is 48. And when x is 4, the volume is, clear up here, 64. So if we go ahead and connect, let me grab a line and connect these values, we can see that we form a perfect line. This is beautiful. And we could go on. So I have an arrow on this end. On the other end, I don't have an arrow. Could we have a smaller base than 1? We could. So we could stretch this down. Let's see if I can grab it and stretch it. But I don't want to get all the way to 0. Right? I'm putting this line as close as I can to x value of 0 without touching it.